Okay, so this video is all about topic 3.2 and it is about modelling a gas. So the first thing is we need to define what actually an ideal gas is. So in this unit we're going to be looking at ideal gases. So an ideal gas is actually a theoretical gas or theoretical model of gases, and we can assume when a gas is ideal that it obeys the three gas laws. There is a separate video about the three gas laws. And what we find with these three gas laws is the relationships that we find between them lead us to the ideal gas equation, which is PV is equal to nRT. And so we can use this equation to model our ideal gases. We also say that all of our ideal gases obey the assumptions that are made. Okay, so we have three gas laws which lead us to the ideal gas equation, and we also link to the assumptions, and that would be what an ideal gas is. So going into then the assumptions of our ideal gas, the first of all is that they obey Newton's three laws of motion. Okay, so Newton's three laws of motion apply to the molecules moving within the gas. We also say that there are negligible intermolecular forces. So negligible means they are so small that we ignore any intermolecular forces between the molecules, so the molecules do not interact with each other. The other one here is that we assume they are spherical with negligible volume. So essentially the volume of the gas molecule is so small in comparison to the volume of the gas. Okay, if we imagine the whole volume of the gas, the volume of the actual molecule itself is so small that we can ignore it. We also say that they have random motion, so they move in many different directions. And that we also have elastic collisions. So remember, with elastic collisions, that means that energy is not lost. Okay. The last one as well is that we also say the time taken in a collision, okay, and that's collisions kind of with the molecules of the side of the wall, is also negligible. So again, the time taken between collisions is so small that we can ignore them. So those are the assumptions of our ideal gases. Now, like we said before, ideal gases are actually theoretical. We actually have real gases, but what we can assume is that we can assume that under certain conditions they take on these assumptions. And so we say, when do real gases behave ideally? So when can we start using this equation for ideal gases? So essentially, when does this start to be true? And the two main sort of points we look at here is we say that this is when we are looking under gases that are under a low pressure. Now, the reason they have to be under a low pressure is essentially we link back to these intermolecular forces here. These intermolecular forces under a low pressure are very, very small. They're very, very weak. They're so small that we can ignore them. They become negligible. Okay. The last one as well is that we also say that it has to go over a high temperature, which basically means the molecules are moving around with lots of kinetic energy. Now, if they're moving around lots of kinetic energy, we know they're going to have random motion. We can assume that the time taken between the collisions is going to be very small because they've got lots of energy. They're moving very fast. They have a high velocity. But also, if they have got a lot of energy, then very small amounts is going to be lost. So we assume it's also negligible amounts of energy is being lost in a collision. So we can assume they are elastic. The important thing to notice here as well for this is that when we say high temperatures, we're actually meaning at temperatures really above room temperature. Okay, we're not looking at the small kind of temperatures close to absolute zero. We're looking really at sort of room temperature for this or above. So high temperature in comparison to 0 Kelvin being our low temperature there.